Hello, so good day to you all. So if you remember from my last video, I had explained a little bit of concepts of pure R, pure L and pure C. That's pure resistor, pure inductor and pure capacitor connected with a AC series circuit. That means connected in a AC series circuit with a AC sinusoidal voltage. So I had ended that video on this note that in a practical circuit, no pure inductor or pure resistor or pure capacitor happens alone. There is always a mix of either two or maybe three of them. So today we are going to address that particular thing in this video. I've taken the screenshots of the last videos, these two particular mm, graphs that you can see here. So as you can see here, so this is for a R plus C load, that is RC load, and this is for R plus L load. What do you mean by that? So basically, if you look at the circuit, it will be something like this. If this is your voltage source, this will be R, this will be C, and this current RC, this current will follow a direction like this. Okay, where the difference, that is phi, between the voltage and the current will not be 90 degree but let's say 90 degree. How it will happen, I will explain using the help of a phasor diagram. Now let us see what is this RL happening here. The circuit will be simple like this. This is V, this is R, this is L, and obviously this will be IRL. RL stands for resistive plus inductive. Here RC stands for resistive plus capacitive. So this current will have a lagging characteristic to the voltage as shown here, which will be not be 90 degree but somewhat between 90 degree. So how come we arrive at this result? We need to explain by a phasor diagram. So let's go to the next slide for explaining the phasor diagram. So first let us take the case of a RC circuit. That means we're talking about this particular circuit. Okay. So in the RC circuit, obviously the first uh, vector that we'll take is the voltage vector, that is the supply. You may be a little bit confused why we are using small v here and but we are using capital V here. So guys, small v is, I've already told you many of times in my previous videos, this is the instantaneous voltage, because the voltage changes with respect to time sinusoidally, as you can see here in both the graphs. V, small v, means the instantaneous voltage, but capital V or capital Vm is the maximum voltage, that is maybe at this point or at this point. Minus Vm means this point, minus Vm means this point, like that. So when you are taking the vector, we need to consider the maximum magnitude. That's why, and obviously the direction. So that's why Vm comes here, or we can simply write it by V. Okay, now let's get ahead with it. So in the previous video I showed that in a phasor diagram where we have only resistor, we have a current which runs in the same direction for the R load only. That means if the load would have been only resistive, if the load would have been only resistive, then the current due to the resistance only would have been in phase with the voltage, and the resistive current would have been like this. And in the last video I also showed that if the load would have been only capacitive, purely and only capacitive, then the current due to the capacitor would have been 90-degree leading to that of the voltage. That means in the coordinate system, we go anti-clockwise, it's a positive direction, so the current leads the voltage. Okay, so IC, that is current due to this only capacitor, becomes 90-degree leading to the voltage. Okay, now in this case, we have this R and C together in the circuit, right? Which means that whatever current actually takes place will be a vector summation between these two currents, and we sum them up, then this will be IRC, which will be the actual current flowing through from the source, the sinusoidal source, into the RC network or RC components of the circuit. That means this angle phi is less than 90-degree in this case. Can you see that? Phi is less than 90-degree in this case. And here you can see that even if the current is leading in this particular graph, even if the current is leading, the phi, I have told it already earlier, it is not 90-degree, it is less than 90-degree, but it is leading. The current is leading the voltage. Here also you can see the current is leading the voltage. Can you see the current IRC is leading the voltage by phi. So this is how we find phi, which is not 90-degree, less than 90-degree, but it is still leading the voltage. This is for a RC circuit. Now what happens in RL circuit? It will just be the opposite. Again, let us take a voltage vector. Similarly, if the circuit had only the R, then the current for the R would have been somewhat here. If the circuit had only L, the current due to L would have been 90-degree lagging for a pure inductor or pure L. Can you see? Do you remember from the previous video? But since we have both of these together in series with this circuit, we need to find out the final current's direction and magnitude by adding vectorially this IR and IL, which will give you IRL, and that is this current which flows from the source to the load. And you can see that this current is basically lagging by an degree of phi, which is the case for this graph. The current is not 90-degree apart or 90-degree lagging from the voltage, but it is still lagging. The current is still lagging. It is not 90-degree, but it is still lagging from the voltage. So this is how practical circuits operate. I'll give you an example. Suppose uh, almost all of you have seen a heating coil, right? A heating coil is made up of things like this, and they are connected to some voltage, right? So this coil has got some resistance. Anything will have a resistance. We know that there is no such thing which doesn't have a resistance practically. And since it's in a coil, so coils give out inductance. Okay, there's the same thing happening here. So our L load happens like this. Okay, this is how the lagging nature of current in an RL load takes place. This is how the leading nature of current takes place in an RC load. Yeah. So now for the last part of today's video, I'll just show you quickly how a circuit which is RLC, that means all the three components present in series, they work, or the phasor diagram happens as per their capacity. So this is R, this is L, and this is C. If they are all of these three are connected in series with a voltage source, then obviously the current will be I in RLC. Now how this current will behave, we'll show it quickly. Now that you have already grasped the concept, I don't think I have to explain much after this. This is the current due to the pure R, this is the current due to the pure L, and this is the current due to the pure C. Okay, now we'll go for two vector additions, one for RC, which will give us IRC, and another for IRL, which will give us IRL. Now finally, we will vectorially add IRC and IRL. It's better to take a different color in this case. This will be, pardon my drawing, this will be your final phi, and this will be your final current. So IRLC will be like this, and this angle, this small angle phi, will be your power factor angle. Please remember that whatever load that you have in your house, or you can see around you, whatever electrical load, it is either a combination of R, L, and C. It is always a combination of R, L, C, and there is somehow this kind of phasor diagram thing is going around, which determines this angle theta or phi, which determines the power consumed by your load. Okay, this thing actually determines. So you can see that cos theta, this I have already explained in the power factor video, that cos theta is dependent on R, L, and C. It is not dependent on V or I. It is not dependent on V and I. So power factor is something which is dependent on load parameters only. Please remember this, guys. This is very important. Power factor is dependent on the load parameters only. That means the power utility, which is giving the power supply to your home, doesn't know that what kind of load or which loads are you going to use. Are you going to use a 20-year-old tube light with a choke, or are you going to use a tube light which is an LED recent one? They don't know that are you going to use a 30-year-old air conditioner with a power factor of maybe zero point 0.6, or a new air conditioner with maybe a power factor of 0.85. So based on that, your actual power requirement in the house changes. It's always advisable to keep appliances in your house with better power factor, because with age any inductance or inductive component increases. If you can see, if this increases, what happens, this current will increase, and what will happen, same here, same here, this will also decrease, and the power factor angle will decrease. Okay, this I am not going to hurry up here. This I'm going to explain in one of my next videos, how the age of an appliance it determines how the power factor gets affected, and how it ultimately implicates your electricity bill. So for now, for today, goodbye. Leave your comments and feedback in the description section below. Bye bye.